This talk has kind of had an interesting genesis over the last few months. Since I proposed it, it has undergone so many iterations and changes. I pushed out an early draft to various reviewers, and they kind of came back and said, yeah, you need to delete 40% of this and rewrite the other 50%. And as a result, I mean, I've been putting in some amazing number of hours, but I'm hoping that where we've ended up at is at least comprehensible with a bit of luck, and perhaps maybe even motivating. I don't know. I guess we'll see what happens. So yeah, what I'm basically pitching, and you might have noticed I've just added the why we need to the front of the talk. The reason why I put my thoughts originally, when I originally did the talk description, is I had a feeling that it would evolve somewhat from when I submitted the talk to when it finally arrived. And I actually have to thank Hartmut for giving me the benefit of the doubt between then and now. So what basically I'm doing is I'm pitching a new Boost library, effectively speaking. More actually a suite of Boost libraries, really. I'm hoping that they're all going to be relatively reusable and adaptable and helpful. But part of what's tied up in the design of these new Boost libraries kind of hangs on one vision of where C++ should go and the Boost library should go. And what I'm going to do is, after I've pitched the general idea, I'm going to make a series of probably fairly contentious claims. And genuinely, I'm actually interested in what you guys think. You'll see that most of what I pitch, I'll put some evidence up. I'll say, here's not very much evidence, but this is the best we could do in the short period of time we had, and what are your opinions? And I'm hoping that there'll be a bit of a debate. And I know a lot of people will be watching this video afterwards to see what you all say, so fingers crossed, might be useful. So the new Boost library is a low-level embedded graph database for Boost. Now by low level, I mean it sits literally at pre-shared library bootstrap. I mean, we're talking core, even before the STL is necessarily initialized. The library is designed to run with header-only STL, theoretically. I need to yet put some unit tests in place that actually test that that's true. But the design is intended that it should run as an embedded level, and it should be able to boot a C++ program into existence. Why might you need that, you might ask? I'll come back to that. Some of the features of the database, and the reason why I'm just going to iterate them out to you rather than explaining them, is because there is an accompanying paper that comes with this talk, and it just goes into all the detail that you could ever want. So I'll quickly tell you what the design is, because it gives you something about what happens later on and informs the debate. By the way, the slides will be obviously online very shortly. So, firstly, what's interesting about this database is that it's really just a bunch of files, literally files in the filing system. All first-tier content is literally a standalone file. So it could be a shared object, it could be a text file. We really don't care. The point is, it can be opened, mem-mapped, and done at that level. First-tier content. I'm not even going to mention second-tier content in this particular presentation. The other thing that it does, which is very unusual compared against other databases, is it takes advantage of filing system specific features. So I just list some of these here. Extents, this is something that Ext4 added that Ext3 doesn't have, for example. Journaling, something that Ext3 has which Ext2 doesn't have. Hole punching is an interesting one. Hole punching lets you look at a file, and you know, if it's 20 kilobytes long, it would normally take 20 kilobytes of storage on the disk space. Well, with hole punching, this is one of those features which filing systems provide that we never really use. You can say, well, I'm going to mark this location to this location, as I no longer care what's in the contents. So you can simply deallocate part of what a file is actually stored in the hard drive. So a 20 kilobyte file can only take 4 kilobytes. This feature is remarkably interesting because it lets you implement a number of locking schemes. So what you basically have is a file that just constantly grows and grows and grows and grows, but its actual physical storage remains small on the hard drive. So it's a very useful way for getting around locking issues, especially over NFS file shares. Copy and write, of course, is something that's been appearing in BTRFS, ZFS. Microsoft ReFS is coming very shortly. This database has been designed to take advantage of that. So when it itself is a copyright on write design, but it will do a cheap copy whenever it goes and makes an iteration. So if you change a single byte in a file, it will literally say to the filing system, cheap copy this, 1 byte to be changed. That way then you take advantage effectively of delta storage. The last thing is bit rot self-healing. ZFS, of course, is famous for that. The reason why it's kind of important is because if you think of an embedded system running C++ or even C, at the minute you usually have to bundle a real-time operating system which has some form of data protection built into it. I think that is unfortunate. I think it would be nice if you could take a FAT32 filing system and put on really strong data protection guarantees, and that's partly where that's coming from. The strong versioning and MVCC concurrency partly built into the security model and also for allowing multiple things to read and write to the database at once. And by the way, performance is terrible for write performance. I'm not aiming for good write performance at all. If you want good write performance, go get a proper, big iron database. Lastly, paragraph content protection, so it can go off and heal some stuff, and it's content addressable, which turns out to be really, really useful later on. And my slides have closed on my phone. Another few minor options. There's paragraph optional ACID transactions. So if you want atomic transactions, you can do that. If you want some arbitrary indexer, so if I want to index my stuff using a weird comma-separated value file, the framework has no trouble with that. I propose simply Boostgraph is the most obvious. You can use SQLite 3 if you so chose. Zip. Basically, the content is quite separate from the indexing. Yes?
Sorry, I have a question for the first slide. Why do you have both copy and write and MVCC?
The question was, why do I both have copy and write and MVCC? The reason why is that the filing system that you're running on may or may not do copy and write and may or may not do a sane locking scheme. So the idea is you provide a generic framework, people extend it as needs. The idea is obviously run a good filing system like ZFS, you can just turn off all of that overhead and let the filing system take care of it. If you're on FAT32, you want everything turned on. Does that answer your question?
Yes.
So the other minor thing which is interesting is it's network shardable. So if you have a particular graph in your local database and you want to send a copy of that particular graph to another database, you can just put it together, package it up, and it sends. The reason why is because the algorithm is actually pretty much Git's algorithm. It's a generic Git-like implementation. I also mentioned earlier that the objects can be executable. I'm planning to use John Bandela's C++ components implementation to allow the executables which provide the graph engine to be stored within the very same graph engine which they themselves access. So there's a bootstrap mechanism for kicking in all of the arbitrary indexers. It's all meant to be self-hosting. And then when you upgrade the engine, you literally do a transaction on the database which binds in a new copy of the engine. It's hard, but it can be done. The last thing there is, I mentioned a lot more of this in the paper. You could overlay levels of databaseness onto the filing system. So you can say, well, this bit of the filing system I'm going to have as just keeping log files, don't really care. This bit contains, super duper important data that must be run out in triplicate and kept no matter what. And the idea is you can just put bits around the place. It's up to you, it's user space, ultimately. So I've done some minor benchmarking. I think it's going to be between 2 and 5 orders of magnitude slower than any of the major graph stores. I don't think write performance is actually really that important. It's mostly read. If you need to write, then great. Thing is, if you've got something like ZFS, because ZFS has got an intent log, you can do about 30,000 synchronous writes per second on the ZFS. It's unbelievably quick. So on that, the database would fly. On something like FAT32, it's not going to. But I'm hoping that at least you'll get 10 per second, hopefully with a bit of luck. And the key part, as I have already mentioned, is that it can do all this before Bootstrap. And the reason why this is really useful, you shall see shortly. So this is the thing. As much as I say it's an embedded graph database, it's really a generic data persistence library. If you want to persist some data in a useful way, this is hopefully the library you'll turn to. And as much as it's big and it's a bit crazy, I'll come back to why I think it's needed. Nat.
Will you say that this is a cross-platform registry in the Windows sense of the word?
That's exactly something I mentioned in the paper. Oh, sorry, Nat asked, is this like a cross-platform registry in the Windows sense of the word? I actually mentioned that in the paper. It's not like the Windows registry. It is like the Windows registry in the sense that it can do key value pairs. What the Windows registry really doesn't have, and it really should, is the ability to link stores across, in other words, it doesn't have any referential integrity. And this is one of the leading causes of Windows failures. I actually have a paper which someone went off and they did a wide-scale study of what causes a Windows system to fail. And a huge chunk is either drivers or registry problems. So the fact that you can now do referential integrity with this is certainly, hopefully, going to avoid that problem. Does that answer your question?
Yes, thanks.
Cool. I'm going to now, at this point, dive out from explaining the graph database. If you want to know a whole load more, there's an archive paper at that address, and these are the section headings. So the reason why I'm going to bail out is because the meat and potatoes is the future of C++. This is where I'm hoping you guys can tell me a whole lot of stuff. So I'll put this slide up at the end. So if you want it, and also it's in the proceedings. So if you go to the proceedings of the conference, you'll find that the paper is already there. So here's the thing. What does an embedded graph database have anything to do with the price of fish, change ripple management, Boost, C++, or anything? Well, those are really good questions. I'm going to go and articulate a vision. I'm not claiming it's the vision, but maybe it's just something that would give us some inspiration when we're thinking about where C++ should go after C++ 17. And if you agree with that particular vision, and I've been running it past the compiler vendors these last few days, they think it's doable. Doesn't mean it's wise, but it's doable. Maybe this might explain why we need one of these databases soon. So I will then provide some evidence, and it's not great amount of evidence. The trouble is that it'd be really great if you could come to Microsoft and say, tell us all about your internal workings, and then we'd have a whole lot of evidence, but I'm not going to give you those figures. So I've ended up having to substitute. So what is the motivating vision? I would like to see a world where we can write C++ as if everything in the wider solution, including all your languages, all your runtimes, everything that's even in related processes, is header only. No matter the size of the program. I'm not saying that you are going to include all the source code when you compile, but what I am saying is that it's going to be as if you included all the source code when you compile. This seems a really extreme thing to aim for. There's a series of reasons why it might be not as crazy as it sounds. The reason mainly why it's a distillation of this, I shall come to you shortly, Chandler, is that if you follow it through, and I have to say Andrew Sutton and Stefan Labaway helped me get to this point, this result is one natural result of a proper ABI management solution in C++. So I'm not saying it's the necessarily result, but it certainly illustrates what's going on. Chandler.
Clarification. Do you include the kernel interfaces, like system call interfaces?
The question was, do I include the kernel/system call interfaces?
More generally, the libc interfaces as well.
Specifically libc, that is an extremely interesting point, and I wish you'd got back to me about an early draft of my paper, because that is a question I'm going to have to defer on. Part of me says that if it's not doable, then I've got something wrong with my design, but part of me also says that that's a huge ask. You know?
I'm also just wondering where you're currently thinking, not anything more than that. So it sounds currently no, but that's fine.
The question was, what was I currently thinking, so where am I aiming at? And I'll be honest in saying that this revelation of making everything header only happened about a week before this conference. Stefan basically kept repeatedly kicking me until the light bulb went on in my head. And then I had to do a frantic rewrite of everything for it to match. And in fact, if you look at the paper, there's a whole section in there where I literally put a bit at the front and say, I just did not have time to rewrite this section. So in that sense, come back to me in a few weeks' time, and I will say that I got as far as thinking in terms of application level, in terms of service level, in terms of C++, but you're absolutely right that if you're going to really test the design, you need to push it to kernel as well, and I need to think more about that. Does that answer your question?
Sure.
Cool. Jens?
17? Shouldn't we move on from headers into modules? Or is it-
I'm glad you asked that. This proposed design, sorry, the question was, should we not include C++ modules and a number of other C++ 17 features? I can answer that quickly. The entire design assumes that what we know is going to be in C++ 17 is already in place. In fact, very specifically, as you'll see later, modules are absolutely crucial to this design working, as in we're going to be generating 100,000 of them. And I don't know if the system can scale, but we'll come back to that. Last question?
Chandler's question was, do you include libc headers? What do you mean by include?
The question was, do I include libc headers? What do I mean by include?
Include them into.
What do I include them into? With libc it's tough because you have a bootstrap problem. And I will simply admit that I haven't had enough time to think about that. It's something which has just literally been raised to me right now. I had got as far as it should work with header-only STL parts, but not the parts of the STL that require runtime components. So I thought at that point you can certainly bootstrap C++ code and anything that runs above that. Libc is a really tough thing. I mean, malloc, if you don't have malloc, it's really hard to do anything in C++, you know?
I'm trying to understand, kind of stepping back, you're talking about including libc into something. What is this something?
So the question was, I'm including libc and
You're saying, are we including libc or not? Include into what? I don't see what the other thing is.
right, you're asking what's libc being included.
Is it like a big blob of that story?
Yes. I'm saying that, I'll come to this actually very shortly, what that means. And if you still have the same question, then I'll happily answer it then. But I think it gets answered in the next set of slides. Any other questions? Okay, I'll just give you a quick bit of code just in case, an example to work through just in case, isn't quite gelled what this means. So I'm going to go and come up with their class foo, and just because I like things that rhyme, I called it a method of boo. I know, it makes me laugh every time. I made it virtual just because, for clarity's purposes, and it takes an int a. So, what's kind of implied in what I just described, and may not have quite clicked on, is that I'm also kind of proposing that build system dramatically changes, because as we'll come to later on, how you go about compiling C++ is different when you make everything header only, as if header only. So what I will say to you is that this proposed design, in the graph database, you can put in rules, and you can say about what happens to ripple changes. So you can say that, if changes happen to this particular type, the following consequences are going to happen, and that propagates throughout the entire graph, and changes those bits necessary, and then returns back to the point of compilation, what's the consequences of your action. So the rule is going to say, and of course I'm assuming here that in C++ 17 we have standard reflect, which of course is currently a proposal on the reflection thing. Maybe we do, maybe we don't. But via this, there'll be basically a little adapter in there, and it takes the class, and it looks and reflects into it, and it goes and spits out some form of Python binding, which looks like this. So it's got class foo, same thing. I've put in 2 descriptors, which say which types it accepts, which types it returns, and out comes boo, right? So it's really, really straightforward and easy. Let's break foo's ABI. So now we've changed the int to a double. ABI is now broken. The rule kicks in, causes all of the recompilation. The bindings are changed over, so now it takes double. And because it now recompiles all the Python code, which has anything to do with class foo in Python, type warning kicks out for every time you use class foo boo with an int, and it says, well, you've just gone and given boo a float, which of course is the mapping of double, but was given an int. So that would happen at the point when you type your C++ code. So you put it in, you hit compile, and it spits out this stuff in code, perhaps hundreds of thousands of lines away from the code that you were typing. I find that very compelling, if a bit mad. But I'll show you in a minute why perhaps it's going to be not just mad, but necessary. So I'll just quickly come over the theory. What I'm proposing is C++ moves from a source file compilation model, so that's where you take an individual C++ file and all the headers that come into it, and we change it over to a type graph compilation model. And in case you're about to ask the obvious question, is that not exported templates? Yes, it is. I'm reawakening the dragon of exported templates. Instead of compiling on files, I'm saying take types, put them into a database, and compile them out. I'm going a bit further though. I'm saying as well that why don't we put a copy of the compiler into the operating system? And why don't we recompile C++ modules a bit like GLSL shaders? The reason why this works is that previously in C++ you really have to supply the source code and you'd have to go from there because any of the intermediate things, formats were too unstable. But if you've got C++ modules in place, and of course we're bearing in mind this is a post C++ 17 world, why can't we just take those pre-compiled sections and modules and any gaps that we need for the particular program that we have, we just shader compile them, lots of them. Reflection, runtime, now turns into a graph query, and to bootstrap a C++ process involves visiting a graph query. In fact, everything just turns into a graph query. Basically, when you come to Bootstrap, you say, this is kind of what I need in your graph, and it matches all of the little tiny C++ modules. You invoke the linker, and poor old, I always imagine Clang, 'cause that's the one I'm most familiar with. Poor old Clang LLVM has to go do something not completely daft with that. And honestly, I'm not a compiler vendor. I did run this past Chandler, and Chandler looked at me as though I was crazy and said, no, I think was your answer. Yep. So, consequences. Instant notification of breakages, no matter how far away. If you ever worked in a very large corporation, you'll find that the trouble with trying to target trunk is that trunk is a constantly moving target. As soon as you've checked out your data, your code, it's moved. You can go off and compile all the code you want, run all the tests you want, but trunk has just moved again. And it's one of the major problems. I mean, I formerly used to work for BlackBerry, and it was just a nightmare keeping your code in sync with everybody else. And you know, we were a relatively small corporation. I struggled to think what it must be like for Google, Apple, or Microsoft. Something that's come as a consequence of this is that a lot of build tools simply go away. I'm not saying that they go away completely, because for backwards compatibility, they're still going to be there, but you can now do optimally minimal rebuild. Because if you're now working the basis of change types, you're calculating the consequences of all those change types, you can do a minimal rebuild, pretty much. And that is a weird thing that we don't have in C++ after 30 years. We're still relying on external tools that go off and grok out an include-based dependency graph, and they just recompile all the source files on the basis that maybe something in there possibly has changed. We do an awful lot of extra work. The vital thing here is that if you've got tens of thousands of little C++ modules, optimization becomes a bit of a problem. It's not that it's a problem, it's just going to take a very long time. And what I was going to argue was that because the graph store can be pushed to and from remote locations, why can't you just push it onto a batch pass or cloud compute? So the stuff that you're developing right now might not be very well optimized, but over time, as the cloud compute comes in and just goes fold, 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 especially the most commonly used code stuff, you could just find yourself speeding up, or you could indeed invoke it by hand. There's some other interesting, yes?
And if you have time, I just want to see that I understand everything, or do you want to just go ahead?
No, please do. Do you understand everything?
So, my understanding is that your graph will just contain the API, basically the type interfaces, and they will reference C++ modules that implement the actual thing, let's say somewhere in the file system or something.
Yes, I agree. Sorry, the question was that that basically the graph keeps a store of the relations between the C++ modules?
Well, APIs, basically. APIs of the types.
Sure, between the APIs of the types. You have to bear in mind as well that C++ modules, they define what a chunk of code does. Where the implementation comes in, I think, is not specified by the standard. Someone can correct me on that. No one's going to correct me on that. Okay, I'm going to assume that that's correct. I think that in practical terms, compiler vendors at the minute basically have an existing system for pre-compiled header generation. It would seem to me to make most sense to reuse some or all of that. And so when you're spitting out the stuff in Gimple or whatever the particular format is, then you do some link time code optimization optionally at the end of it. That seems to me to be the best way. Now, I stress I'm not a compiler vendor, and I'm just understanding from my best understandings of that.
So
Kevin.
Following up on that, your comment about optimal optimization there, what you've proposed here assembles the program at runtime.
Correct.
So all of the state-of-the-art work that's happening in optimization is whole program optimization. So you can't push that off to a batch process somewhere unless you know every component that's going to be loaded at once in runtime, and then that's optimized together as a cohesive unit. How would that be impacted by what you're talking about?
Kevin said that how does this fit in with, if you've got all of this work in place, then how do you optimize all of this if you're going to push it off to a batch pass? Because you'd effectively, as if I understand correctly, you'd have to upload all of it to some remote server, and then they would know the full amount of it. And then they have to do the batch pass optimization and then collapse it back down again. Is that what you're saying?
Well, it's more of what you've proposed decides what's going to go into the program at the last possible moment, which means you can't do any of that whole program optimization until the results of that decision are known.
Okay. So the question was, because you're leaving all of the code assembly to the very last moment, it's very hard to
To do global optimization.
to do global optimization. Yes. I agree that's absolutely a very valid point. One of the things I pointed out in the paper was that maybe this is a debug-only thing, because in actual fact, knowing what stuff's broken as a consequence of your change is something you probably want to know at debug time, and you actually don't care about at release. So one perfectly valid implementation of this is this purely debug outcome, and then when you switch into release mode, you dispense with all of this, and you compile it the old-fashioned way. And I think that's absolutely a very likely outcome. I mean, in the end, you're just looking to know what you've done if you've broken someone else's code, and go from there. Chandler?
I just wanted to point out that what you're describing is essentially somewhere between the Java machine model and the lifelong program optimization that Chris Latner and Vicar and I proposed in Chris Latner's master's thesis. And it doesn't have any of the problems with, like, the whole point is that if you push it out for optimization after you form the program and start it running, you can do cross-module optimization. You can even get runtime feedback into your optimization as long as you're willing to pull the results back down and replace it in place. Then it's fine. Of course, no one has ever managed to implement a large system like this and have it running practically. But
Doesn't mean it's impossible.
doesn't mean it's impossible. That's like the theory is well laid out in Chris Latner's master's thesis.
Right, so Chandler basically said that everyone already knows this proposition, and it is
Let's talk about the optimization stuff.
just the optimization stuff. So the optimization part of doing very late stage optimization is well known, and he was saying that it doesn't really scale out to very large systems yet, and maybe it might in the future, but no one really knows.
Well, I would more say I don't think anyone's tried.
Just to repeat back, no one's really tried, is what he's saying. And I completely agree with all of that assessment. And as I mentioned, I'm not a compiler vendor. You're next.
Going back to your change management and detection, seems like you're only concerned with the interface changes, but the other big part is the semantic, behavior changes, and it doesn't seem. Do you have anything for that?
The question was, I only seem to be concerned with API changes and not semantic changes.
Changes.
Sorry?
Behavior.
The behavior changes. I agree that that is entirely an open question, and I haven't got to that point yet either. I mean, I just originally started off trying to explain why I thought a graph store was a really, really good idea, one that was at embedded time. In terms of justifications, because you're talking about stuff in 10 years from now, who knows what the technology is going to be like in even 5 years from now, let alone 10 years from now. I mean, some of the remaining slides that come will show some of the trends that are coming in terms of hardware and software and that's going, and maybe that might explain some of where we're going to have to start showing more attention. In terms of answering your question, I don't know is the answer to that. Nat?
I just wanted to add a point that I think I heard Chandler say, which is that while nobody has yet implemented the very late whole program optimization, the theory is in fact well established.
Yes, Nat basically said that while no one's implemented whole program optimization at that large level, very late binding whole program optimization, the theory is well established. I'm not an expert in any of those areas, but I think it's you and Chandler would know a lot more about it than I would.
Just I'm quoting from what I heard him say.
Oh, okay. One more question? Yeah, sure.
Less of a question,
more of an encouragement to talk some more. What you've described so far, for me as a simple developer, what it looks like is a yet worse version of DLL hell.
I come back to that. I'll just say the question.
Yes,
Yeah.
so I very much want to hear that response.
The question that was that you said that as a typical developer coming and looking at this, he just sees an even worse version of DLL hell. I completely agree that it could look like that, but I've taken significant steps to prevent DLL hell ever happening again. Because I hate DLL hell. I think versioning, as soon as you start versioning an ABI, something's probably already gone wrong. And this is where partly the graph store comes in, because you can start encoding rules to say why we never need to version ever again. I had this idea of concepts for the binary level. So you basically set a series of rules to say what should be the consequences of changing code. And that should theoretically eliminate ever. In other words, the bits can be recompiled that are safe to recompile, but the bits that are held static, because there's a platform SDK there, that never changes. And as soon as you try to change anything that breaks it, you get instant error message and you won't be allowed, commit your code. I'm sure BlackBerry was not alone in that it's very easy to break the platform SDK API. You go off and you make a change and you fix a bug, and then before you know it, SDK has been broken. And then the people who check that basically have to say, can you undo your change or do something else with your change to make sure that ABI has gone back to the way it should be. And I'm sure that's the same with every large corporation. Does that answer your question?
I'll keep listening.
Okay. All right, so there's about 15 minutes to go. So here comes the more contentious stuff. Oh no, I forgot this part. Basically, there's something implied in this. You can actually get easy C++ components, and not like Banderas components, not like COM components. These components are literally rules in the graph store that say what to do with ripples. So I was just mentioning that there with BlackBerry that one of the handy things would be that you set the rules up, and at the point of compile it says, you can't do this. And then you have to go back and change it without some human having to check it. It's all done at automated time. A big thing that I'll come back to shortly is that this proposed system stops using the C symbol namespace for C++. One of the big things that C programmers get really upset about with C++ is that it spazzes a whole load of stuff all over the symbol table. If you ever look at Linus and him not letting C++ into the kernel, I think a lot of it is just how messy it all looks. I think we could do with moving away from reusing that. I think we can keep it as a compatibility part, don't get me wrong. But if we can get most of C++ off that, I think that would be a huge benefit to how it looks from the outside. And something I mentioned earlier was that this is an ABI management solution fundamentally. This is just the hook to get you all interested in thinking about it, but the real power of it is managing ABI, and that's where I'm really heading for. And I'm going to mention other programming languages I think would be very, very interested in this. I talk about that a lot more in the paper, much less here, unfortunately. So the question, of course, is why? And I'm going to be slightly controversial. There's not many people who come to a C++ conference and say the following things. I'm going to provide some evidence that C++ is in relative decline. I'd be really interested to see what you all think about that. I'm going to also make some evidence that shows that Boost is in both an absolute and relative decline, and I'd be interested in seeing what you all have to say about that. I'm going to argue, and by the way, these are claims I'm going to return to, so you don't have to ask questions about them now. Have a look at the evidence, and then I'll certainly be interested in seeing what people say. I'm going to argue that we need to start returning to becoming a better systems programming language. One of the really interesting things at this conference, if you ever go here and you look at all of the talks being here, is that there's an awful lot of Haskell turning up. There's an awful lot of compile time stuff happening. And I have no problem with that, by the way. I am just as interested in weird move semantics as anybody else. But think of it from the point of view of a guy, say he's an engineer working on the Python runtime, right? So he looks at C++ 11, and he says to himself, what does C++ 11 provide me, which C11 does not? And that is a really interesting question. Because if you go down through the feature list of all the stuff that was added in C++ 11 and all the stuff that was added to C11, you cross the two off because in the end from the Python runtime engineer, he's going to use the C11 stuff. And you look at what was new that was added that's going to make that Python runtime engineer get really excited. I think I could find, when I did it, one item, which was alignment. Because at the minute, Python runtime engineer, he has to do a bit of alignment management, and C++ facility are somewhat better than C11's. I can't find anything else. So from the Python system engineer, by the way, if someone can think of things that are in C++ 11 that C11 does not have, which would make a Python systems engineer very happy. I'd love to hear them. But I think from what I'm trying to drive at is that C++ 11 and 14, there's a lot of really great new features in there, and I'm extremely happy to see them. I'm sure everyone at this conference is. But thinking at it from outside, coming at it from a Python perspective, from an Objective-C perspective, from anyone who's not wrapped up in the C++ namespace, C++ 11 doesn't really look tremendously great. It doesn't provide anything that's really killer feature. It doesn't really transform any use cases. It's great for C++ programmers, but for the Python programmer, I can't think of much. And this is a serious question, because if you look at the popularity of C++ and where it's going to go into the future, you've got to start asking yourself, are we a systems programming language, or are we a niche programming language for async and for maths? Because that's what we're turning into. If you look at all the major developments been happening in C++, in terms of new libraries, where all the action's at, it's hedge funds, it's people doing low latency work, it's not for writing operating systems, for doing systems programming, not like it used to be. And if we were to refocus on the systems programming stuff, I think this would be a really, really valid thing to do. And of course, as I pointed out, I think we need some signature projects for C++ 11.14. Things that really showcase the new language standard and really demonstrate why C++ is the most important thing going forward into the future. That's my hope, anyway. So, just in case anyone, actually I'm really surprised no one's asked this question. Why this instead of doing more code per compiland? I'm really surprised no one asked that yet. So, cool, I can probably answer that one really quickly. This is a graph from Herb Sutter's paper, 2009. I think it's been updated. No, it has been updated. I think it was originally a 2003, 2004 paper. So basically Herb was arguing that clock speed growth has basically tailed right off. So if you look here at the clock speed growth, it's gone linear. It's no longer going exponential. So far, transistor density keeps going up exponential. So that was up to about 2009, and that's literally, I copy and pasted that from Herb's paper. Here's an interesting graph that came from Global Foundries. The red line is the advertised process size for hardware. It keeps going down, as it needs to, because we need to say we have a 15 nanometer process. The orange line is the half gate width. So this is the how thick the wires are. That's on the actual CPU. Notice the fact it's just gone linear. The new 15 nanometer process, if that's the right, it's 14 I think actually. It actually uses 22 nanometer gates. So the wiring is all wired up with 22, while they're claiming that the process size is shrunk. And the yellow one's the transistor size. And the reason why it remains relatively flat is because they've been building them up 3D. So they can't shrink them anymore in 2D, so they've been extending them into 3D space. This is really interesting because if the wires can't keep shrinking, I can see that Moore's law is going to start stopping sooner rather than later. Now, we don't know. I mean, obviously, if you ask the big industry people, they're pretty confident they can get to 2020, but after that, who's to say? Here's another interesting thing. Blue line is magnetic storage, running right back since the very, very beginning. So this is the amount of capacity per inflation-adjusted dollar, and I keep this because basically I'm an economist as well as a software person, and I find this stuff interesting. And the red line is flash storage. So you'll see that flash storage, because it's tied to transistor size, it's going to taper out pretty much where transistor sizes are going to taper out. But we've still got an ongoing increase in magnetic storage. So this presents a really interesting future conundrum, because if CPUs are going to stop increasing in power, and RAM is going to stop increasing in size, but the ability to store data is going to carry on increasing, albeit not quite as exponentially as before, then I think Chandler made a really good comment about this when I mentioned this earlier on this week. It makes companies like Google who do search indexing, it makes their life very tough going into the future. It is hard to see how you're going to scale to indexing the world's information in that kind of world. For us C++ programmers, I'm going to make these following claims. I'm going to claim that the cost of including ever more source code per compiland stops being sunk by transistor density growth. I think that's a fairly non sequitur. I think what's going to happen then is build times are going to start rising instead of falling with time. One of the great troubles that we've had is that we've had it really easy over the last 30 years, because you write some code and it takes forever to compile, but next year is going to be quicker, the same code. The following year after that is going to be quicker again, because processors are always getting better. If processors stop increasing in performance, then we're going to carry on adding new code because that's what we're used to doing, and we're expecting in 3 years' time it's going to be faster. Well, it ain't going to be faster. It's going to stay as slow as it ever was at the point that you wrote it. And if you think about how that changes the economics of software production, and how everything in terms of planning out a build schedule into the future, in terms of product cycle, that all completely transforms. Because if code is going to keep at a fixed level in terms of compilation, it all just transforms. So I'm going to go and make the following claim, is that I think that C++ probably, as best as we can understand, is going to start looking a bit more like the 1990s. So in those days, processors were really slow. So what you did was you did lots of little small compiles and then you put them into a linked layer, and the linked layer was incredibly simple because having to link all that code together was really hard for those computers of that time. And that's my best estimation, because I just can't imagine a world where CPUs aren't constantly improving. The only difference is that we have all these fancy C++ techniques. So if you look at the symbol count that's output by modern C++, it is just astronomically higher than the symbol counts that were output by the same volume of code in the 1990s. I mean, mainly templates. Templates produce a fortune of little bits of code. So that's my claims. I'm also going to make the following claims about effects. And I have about 4 minutes. I reckon that when this happens, CPUs go linear. What's probably going to be the consequence for most shops, they're sitting there with a Python stack, they're going to go, well, we need more performance. So they're probably going to say, we're going to have to start rewriting large chunks of our code into some systems programming language to get that last bit of juice out of the system. And the question then becomes, is that going to be C++? I think we're going to be big return. C even is going to see a lot more stuff. And I reckon probably, at the present set of trends, this is going to happen about 2017, 2020. By the way, in case anyone asks about graphene or phosphorine transistors, they're just not going to be ready by 2020. They're great, but the R&D that's been put into them just isn't sufficient. So here comes the next question, with 3 minutes to go. Is C++ going to be that major systems language into the future? And I think everyone at this conference hopes that it will be. So here's some interesting figures. This came from OLO, and this purely refers to open source software. But this is the trend, according to their parser, which may or may not be good, of the different languages in terms of the total number of developers who have contributed at least one line of code in a given month. So this is an estimation of the number of developers working in open source over a period of time. And I took the following languages: C, C++, Java, JavaScript, Perl, PHP, Python, Ruby, mainly because they're the most popular ones. And as you can see, running up towards the recession, times were good in open source. The recession hit us all pretty badly. And since then, there's been a sort of weird thing where JavaScript is really, really popular, but everything else isn't. You might notice there's a little dip just here across the board. That was Hurricane Sandy. So when Hurricane Sandy happened, there was a really noticeable statistical deviation in the amount of open source that was being done. It shows how important the New York area is to open source. So I mentioned earlier on that I've been claiming that C++ is in relative decline for a decade. Well, here's a graph. Again, this refers to open source, and as a result, these figures can only really be born to that. This line is C, this line is C++. Both have been in decline. Stabilized around about 2010. There's a bit of an uptick there around about 2012, and went down again. Would that all match up with what everyone's been kind of feeling? Chandler.
So, you showed me these statistics, so I'm cheating. I had more time to think about them.
Good. That's why I showed them to you.
The monthly contributors, percent of total. So the fact that the percentage of contributors from C++ is declining could mean C++ is declining, or it could mean that the total open source contributors are increasing. And thus a steady state number of C++ contributors declines in its percentage.
Well, this is why I showed the total absolute, sorry to answer the question. He was saying that the absolute percentage may be an artifact of total number of open source developers going up, and therefore the total number of C++ developers might be relatively static, but would appear to be dropping. This is why I showed the absolute numbers graph. And you notice there for the last 2 years, the entire open source appears, according to OLO, to be in decline across the board. I don't know what's going on there. I did look into it, and it looks like they haven't broken their compiler or their parsers. So I agree that that's a valid point, and it would be really great if, let's say, a large multinational funded an academic to go really look into this matter and really get the figures. I can think of one particular multinational in question. That'd be a really, really useful thing to do, but I have no power in that area. I think what happens in open source and how that affects the Silicon Valley bubble, which of course it's in, I think they're intimately tied. I think it'd be really useful to find this stuff out. The only trouble is that usually most academics take about 2 years to find out, and by then the data's out of date. John?
Just a couple of comments. One of like about the total number of monthly contributors. It's looking, it's not looking necessarily at other people continuing to contribute. It's probably a lot easier just to contribute like a snippet of code to JavaScript or whatever than it is to actually get a piece of code integrated into an ongoing open source C++ project. The other note on there is the only two systems level programming languages are C and C++, and they're both tracking about the same. And if you're talking about the return to systems languages, like I said, we're not like falling behind C. We're still like the only, along with C, the only major like systems programming language that's in like the top 10.
Right, so John made a number of points. He pointed out that it's easier to commit an odd line of JavaScript rather than get a line of C++ into code. I don't know if that's true or not. I know that seems probably likely to most of us at this conference, but without facts, we can't say one way or another. The second thing he said was that the only two systems programming languages that are on this graph are C and C++, and that the relative share between C and C++ has been remaining static. If you actually look at this, I would answer to that they've actually been very much converging. Whether that's because of weakness in C and strength in C++, I don't know, is the answer to that. As I said, my facts and figures are very unsupportable. Again, it'd be really useful to know. I hate to be not that useful. It's now 2 minutes past time.
I want to add one more thing there.
Sure, Kevin.
This is something that I've been dealing with for years, being in the open source community as well. Statistics that come like this, statistics of what languages are being used on GitHub, et cetera, you cannot actually draw any conclusions from them whatsoever, because there's no way for them to incorporate the relative importance of the repository that stuff was put into. So somebody contributing 10 lines of code to, I don't know, Nginx is significantly more important to the global open source community than some guy who, put together some tiny JavaScript library that 3 people use and he publishes on GitHub. So not that I'm saying that's not a valuable thing, it could turn out to be something very valuable, but there's absolutely no way for any of these aggregators to take any of that into account. So, for example, the reason JavaScript is so popular is because thousands and thousands of people are putting together tiny JavaScript things and publishing them all over everywhere, but they don't actually change the value of the world's open source code in any measurable way.
So Kevin was basically saying that some pieces of code are vastly more important than other pieces of code, ultimately, and I completely agree with that. And it's very hard to disaggregate from this which bits are more important and which bits are not. I would say in answer to that, can that be calculated? It can be calculated for something like GitHub, fairly straightforward. For something that's not on GitHub, it's a bit tougher, and GitHub is not a very good representation of total open source software out there. It's a very, very biased slice.
And
So
you can't calculate it from GitHub either, because you can only calculate popularity of contributions on GitHub. You can't calculate how much that code is used in the world. Because there's no way to do that. It's open source. So you have a dilemma that you can't fix.
Sure. And I mean, he's basically saying that it's very tough to basically map out these relations. I would actually say that probably the most important piece of open source software I can think of is Zlib, actually. If you look at how often it's used and where it turns up, it just turns up everywhere. And it's a change of line of code in that has profound consequences over a huge code base over time.
Or OpenSSL, as we all know.
Or OpenSSL, as we all learn to our cost. Yeah, absolutely. I'm going to skip a whole lot of stuff because I am now 4 minutes past time, and I hope that we'll push to questions for anyone who's interested. But I'll skip past this, and we're now on to decline of boost. So I'll quickly run over these figures and then I'll let you all go. Here are the total number of commits per month. 2008, roughly up to about 2011, you were seeing about 1,000 commits a month. Since then, we're now dropped down to about 500, and the reason why it's tailed off down here is because of the Git conversion. So after SVN was turned off, it obviously went to 0. Here are the total number of contributors contributing to Boost. Once again, you'll see between 2008 and 2011, you had about 50. Since then, it's been trending downwards, and it's now down to about 30-ish in terms of regular monthly contributors. Here's the total number of libraries added to Boost. So I've separated them out into general purpose and single purpose libraries. The distinction is very easy to know it, but without being able to describe it. General purpose would be something that solves many problems. Single purpose is something like Type Index, which I review managed only quite recently, and it does literally does one thing. So if you look at the total number of libraries being added, 2013 was obviously a pretty bad year, 0 libraries added. The 2014 figure is the ones that have been provisionally approved. And that general purpose library, and whether it's going to be actually approved this year or not, I would doubt. I think it will push it into next year. So that's what I would qualify as this.
Just to clarify, that's the reviews accepted rather than when the libraries were added.
That was when the libraries were added, actually this graph. So the reviews will be accepted and say that it's fine, but it may take a year for the library to actually enter. And when I calculated these figures, it was on the basis of when they actually entered.
Oh, when they entered.
Yep. So 2013, I mean, I know with the Git translation it was a bad year, but it was really, really tough going. Last bit of figures. I went and calculated the total number of posts to Boost mailing list. This is the dev list, and this is the users list. I think it just speaks volumes, what's happened with the graph here. Users just aren't really posting that much anymore. Even devs have seen, again, it's around about 2011, there's been a significant tail off. And this is when I say that Boost is in relative and absolute decline, and I get into an awful lot of trouble on the mailing list. I think this is a strong indication why.
I think you could draw that same graph for any mailing list that has been alive that long.
I would the thing was, you could draw that graph for any mailing list that's been alive that long. I will double jeopardy that. If all open source has been declined for the last 2 years, which the previous OLO graph suggested, then maybe this is a result of the global open source downturn and has nothing to do with Boost whatsoever, and therefore Boost does not decline at all.
I'm just saying most developers that get interested in open source and want to talk about it do not subscribe to mailing lists anymore.
He said
This is like a very 90s thing apparently, and everybody wants to talk on web forums now.
he was saying that most developers nowadays don't want to subscribe to a mailing list because it's a very 1990s thing, and they want to go through a web forum. I would answer that with saying that I can see that for Python programmers. I struggle to see that for C++ ones.
Stack Overflow, and I bet it does not decline like that.
You said there that the posts to Stack Overflow don't decline. That is a really interesting question. I tried to find out some figures for this talk. To calculate that was hard because the tags that you get applied to things, unfortunately there's a lot of them, and you can sit there counting them all up, but then you find that they've been double counted and you can't separate them out. So I gave up, I'm afraid, before this talk. But I'd love if we could write an API program that literally did some hard grafting to find that out, because that would answer the question. Yes. Yeah.
I don't want to nitpick your numbers here. I mean, I know it's very hard to get any kind of numbers. I would just add that I kind of have the subjective perception that the general point you're trying to make is pretty much true. And I think that I'm not the only one that feels that way. And I also think that we're becoming aware of it and that we're trying to address it. So I don't see it as something inevitable. I see it as more something that is partly, we've got new C++, we've got, Boost has gotten large to the point where we're having trouble scaling and things like this. I don't know that I'd attribute it to any fundamental tectonic change as opposed to more particular Boost problem.
Well, I'll quote an engineer from this conference. This is a highly respected engineer, and he said, Boost used to be about all the stuff you really wanted in the standard. Now Boost looks like all the stuff that wasn't good enough to get into the standard. That was not me. That had a fairly hefty response in the mailing list, to put it mildly. But I think that just captures a very big reason why people, when they're thinking in terms of Boost, They're not seeing what they used to see.
Well, and also the thing, since times are changing, it's really not clear, and we're talking about scaling, it's not really clear that the standard needs to grow as fast, and maybe it's not even a great idea. So the whole concept or characterization of Boost being the antechamber to the standard, I'm guessing is part of the problem perception, because it can't continue to be that.
Absolutely.
It's going to have to evolve. And evolution, well, maybe decline is part of evolution, but one thing is for sure, it's not going to be what it was 10 years ago. So, and it can't be what it's going to be 10 years ago. It's going to be different. It might look like decline to some people. It might look to revolution to someone else. It's hard to tell. So, but I think that decline maybe is a little bit inflammatory, but I would definitely agree, and I think that your numbers sort of suggested, although I don't know they prove anything, that we're in a state of flux. Things have to change. We have a lot of people that have expressed this viewpoint, including this well-known person, and I think that we're actually in a good place, but we're really not quite sure which direction we're going to go. But it's going to be. I also believe things have come together that it's going to be something like no one's ever seen before.
I hope so. I genuinely, really, really do. Joe.
The other stuff is that, 10 years ago, Boost was some kind of spirit to actually have a pressure force on compiler vendors, because people were eager to use what Boost has to offer, and they were bitching about the compiler vendors so that compilers get fixed, and so Boost can compile it and can use it. And after a while, and I think that's due to the success of what has become C++11, and as you say, that most of the stuff that Boost used to be is now into the standards, this pressure is probably left down. And I think that it should be great if we become again this kind of, pressuring force on compilers by pushing more C++11, more C++14 library, so all compiler vendors get their hand on their pockets and make the standard support complete, and so on and so on. I think that's where we were, and we succeed, and I think that part of this decline is because we succeed. Now I think we have to find another objective and go push this way.
Yeah, we're basically victims of our own success.
Yes. Yeah. I completely agree with that. I would say that there's two parts of new features like that. There's foundational stuff like shared pointer and optional and expected. That kind of stuff, is everyone's really, really interested in. But there's much less of that to be added to C++17 than there was to 11, So that stuff is kind of past. We can't really do much more of that in the future. What I would say, though, is that if you were to broaden the remit, as you just pointed out, to libraries that really push the language to its limit, I think that's a very interesting way of seeing a future for Boost, in my personal opinion. So I, in other words, basically agree with you. But I can see that there's a lot of difficulty between what do we actually define as all of that,
Yeah, exactly.
It's really tough,
All the low-hanging fruits are actually being picked.
All the low-hanging fruits have definitely been plucked, yep. Although, if you looked at the talk on expected, it's remarkably hard to do expected in a way that's correct. It's really, really tough. And, yeah,
That raised other questions.
Yeah, that raised other questions. Thank you very much anyway for coming.